Okay, so let's continue the course. Okay, so I come back to what I have done. Okay. Just 1 second, okay. Okay, so what we have proved. So we are interested in proving that this limit sup is equal to plus infinity. What I have proved for the moment is that remarking that the limit set I am interested in is equal to this one for any s strictly positive, okay, because this tends to 0. I can prove that R is independent of all this one, okay? It implies that the limit I am interested in is independent of this sigma algebra here. That is what? I remind you that this is sigma of BU for U between 0 and S. And this is true for any S belonging to R plus here. So I can deduce from this one that R is independent. So since it is independent of all this one, so of the smallest sigma algebra that make the BU measurable for U between 0 and S, and I do this for any S, it will be independent of sigma of BU for U that is positive. But I have not a problem, but I have to remark that R that is made, so that is this limit sup that is made from the Brownian motion. Of course, it is measurable with respect to this sigma algebra because it is the one that make all the things related to the Brownian motion measurable, in fact. So this one is also sigma of BU measurable. And so we are in the situation where R is sigma of BU for U greater than 0 measurable, and R is independent of the same sigma algebra. So I can deduce that R is independent of R. And what is the meaning of this one? This one implies that R is constant. It's a classical result of probability theory that tell you that if you have a random variable that is constant with itself, and that is independent with itself, it is necessarily a constant. But be careful because here, in my particular situation, constant means that I belong to R, I am a constant number, or I can be infinite also. Okay, constant and mean finite number are always equal to plus infinity. So if I want to conclude, in fact, knowing the fact that R is constant, I just have to check that R can't be finite. Okay, so it's what we are going to do. So I am here. I erase. So we have to prove that now R is not finite. So suppose the contrary. If R is finite, it's a finite number. I said that by definition of the limit sup, if I have this, okay, necessarily the probability that bt over the square root of t is greater than R plus 1, this one goes to 0 when t goes to plus infinity. So why I have this? But in fact, if you are fluent with the limit sup, it's just a consequence of the definition. Keep in mind that R is equal to the limit sup when t goes to infinity of bt over the square root of t. So why I have this? If I don't have this, so what is the meaning of this limit? It means that I goes to 0. So for all epsilon strictly positive, there exists an m such that for all t greater than m, okay, the probability that bt over the square root of t is greater than r plus 1, this one is less than epsilon. Okay, so this is the definition of the convergence towards 0 when t goes to plus infinity. If I don't have this convergence, it means that there exists an epsilon strictly positive such that for all m, there exists a t greater than m such that the probability that bt over the square root of t greater than r plus 1 is greater than epsilon. Okay? And so if I don't have my convergence towards 0, okay, it means that I am in this situation. And if I am in this situation, it should be possible for me to build a subsequence of Tn converges. So there exists a sequence Tn converging toward plus infinity, and such that the probability b of Tn over the square root of Tn greater than r plus 1 is positive. And this is in contradiction with the fact that the limit sup is equal to r, because if I have this, it implies that the limit sup is necessarily greater than r plus 1, something that is not possible because I know that my limit sup is equal to r. So it implies that this one is not possible. So I have this one that is exactly to say that this probability converges towards 0. So if r is finite, I have necessarily this term that converges towards 0. But I have a problem with this one. Why I have a problem with this one? Because what is this probability here? I write it here. The probability that bt over the square root of t greater than n plus 1 is what? By this probability, what is the distribution of bt over the square root of t? It's the probability that n01 is greater than r plus 1. And my Gaussian distribution, okay, here, it's such that the probability to be greater than any number is necessarily strictly positive. So it's not possible for this term to be convergent toward 0. Okay, so if I summarize, I said the following. If r is finite, then I should have this convergence. Okay, because if I don't have this convergence towards 0, I have a contradiction with the definition of the limit sup, what I have written in red here. So if r is finite, I have this, but this is not possible, in fact, because of my argument here. So r is not finite. So r is equal to plus infinity. And if you come back to what I have done previously, to say that r is plus infinity is exactly the result I want to prove, because r was defined this way. Okay? So I have proved the fact that the proposition 1.3.4 hold, and more than the part concerning the green relation, okay, what is interesting to have in mind is that I have used the transform of the Brown motion to prove the black, the blue, and the red. Okay, so we have a very important corollary of this proposition that will be another strange property of the Brownian motion. The fact that the Brownian motion trajectory is P almost surely nowhere differentiable from the right and nowhere differentiable from the left. Okay, so it's what we are going to prove now. It means that, okay, you have no point in the Brownian trajectory with probability 1 such that I am right or left differentiable. So you have here an example of trajectories or mappings that are continuous because the Brownian trajectory are continuous, but nowhere differentiable. Okay, so I continue here because it's my slide. So let's do the job here. I copy this one. Make it here. I have this one here. It will be bigger. So here I want to prove that, okay, the Brownian motion is nowhere differentiable from the right and from the left. Okay, so just have a look. I just want to check that I have done good manipulations here. Where I am here. Okay, yeah, it was 11. It's okay. So I am proving the corollary 1.3.1. So first, we are going to prove that I am not differentiable from the right at 0. Okay, so if I am interested in the right differentiability as 0 of the Brownian motion, I have to be interested in the limit of bt minus b0 over t minus 0 when t decrease toward 0 plus. Okay, it's what I am interested in. Okay, and I want to prove that this limit, okay, I want to prove that this limit doesn't exist. So suppose the contrary. If the limit exists. What can I write? I can write that bt over the square root of t is equal to bt over t multiplied by the square root of t. Okay? This one goes to 0 when t goes to 0. And I have supposed that the limit exists for this one. Okay? And so it implies for this that if my limit here is a finite number, if I multiply by something that converges towards 0, the limit when t goes to 0 plus of bt over the square root of t is equal to 0. But I have a contradiction. It's not possible. No. And why? It's not possible because I have proved this. I have proved that the limit sup of bt over the square root of t is equal to plus infinity. So it's not possible for this quantity to converge when t goes when converge towards 0 plus, because if I have this, it will imply that the limit sup will also be equal to 0, and it's not what I have. Okay, so I have proved that the Brownian motion is not differentiable from the right at 0, because I have proved that if this limit exists, okay, I have a problem with what I have proved in proposition 1.3.4. Okay, so I am not right differentiable at 0. Okay, so it's the first step. I am not right differentiable at 0 for a Brownian motion. Okay, so let's continue. I have this here. So now we are going to prove that we are not right differentiable or differentiable from the right at any point t0 belonging to R plus. Okay, so I am not right differentiable at t0 for any t0 in R plus. So it means that I have to prove that the limit when t decrease toward t0 of bt minus bt0 over t minus t0 doesn't exist. It's what I have to prove. But keep in mind the following. We have proved together, so it was here maybe, we have proved that if I transform the Brownian motion these 4 ways, I still obtain a Brownian motion. In particular, this one is a Brownian motion for any s, in particular for s equal to t0. Okay, so it means that the process bt plus t0 minus bt0 is still a Brownian motion. Okay, so let's come back to my point, and we are going to use this fact. I know that, according to what I have said, that b t0, that is defined this way, this one is a Brownian motion. And according to what I have done previously, I know that a Brownian motion is not differentiable from the right at 0. A Brownian motion is not differentiable from the right at 0. So it implies that the limit when t decrease toward 0 plus of bt t0 minus b0 t0 over t, this limit doesn't exist from my previous step. But what is this quantity here? This quantity is what? It's b t plus t0 minus b t0 over t. Okay, that may be written if I write s equal to t plus t0 as bs minus b t0 over t, that is equal to s minus t0. Okay, so I know from this fact that the limit of this term, okay, that is the limit of this one when t goes to 0, okay, is equal in fact to the limit of this one when s goes to t0. Okay, so I deduce from this one that the limit when t goes to 0 plus of bt plus t0 minus bt0 over t is equal to the limit when s decreases toward t0 of bs minus bt0 over s minus t0. I know that this limit doesn't exist from this fact, and so this one doesn't exist. And you see that this one is exactly the one I am interested in. So I have proved that this limit doesn't exist from this argument here. And so I have proved that the Brownian motion is not differentiable from the right at any point t0 belonging to R plus. Okay? And the argument that is important here is that I did use this property for any t0, so the right differentiability at any point t0 belonging to R plus is a consequence of what I have done in the previous step, that is to prove that I am not differentiable from the right at 0, and to apply this to this transform of the Brownian motion that will allow me to pass from 0 to t0 doing the translation, and the translation is inside the definition itself of this new process. Okay, so I have the fact that a Brownian motion is nowhere right differential. Okay, and the only point it remains to prove is that the Brownian motion is nowhere differentiable from the left. So I continue. I have done the job for the right, for the left. I erase everything, and now, so if I study the right and the left differentiability, okay, so here it's no more the right, it will be the left. Me from the left here, okay, at t0, but here t0, if I am from the left, okay, t0 is in R plus star, okay, because the Brownian motion is defined on R plus, okay, so I can't study the left differentiability at 0. Okay, so I have resolved concerning the right differentiability, and now I want something concerning the left differentiability. What can I use? But I can use, once again, a transform. Okay. So if I come back to what I have done previously, that was this point here, we have seen that all these transforms are still Brownian motion, and I have among the four here one that allow me to reverse the time. And to reverse the time is exactly what I want, because, okay, if I study the convergence from the right, if I reverse the time, I will have a convergence from the left. Okay, so to pass from a convergence from the right to a convergence from the left will be through a change of time that will be allowed by by zt here. Okay, zt. So from the previous step, okay, zt, that is a Brownian motion, is not right differentiable at any point belongings to R plus. Okay. Okay, so I have this. So in particular, okay. So for all, let's say S0 belongings to R plus star, the limit of zt minus z S0, oh, I will write it this way. I will change my thing here. The limit of zs minus zs0 over s minus s0 when s decrease toward s0. This limit doesn't exist. Okay, because I am not right differentiable at S0. Okay. And by the fact that Z itself is a Brownian motion, so I can use, okay, what I have done in the previous step. So let's have a look on what I have here. So let's come back to the definition of ZT. Okay, so let's have a look on this. What is ZT here? ZT here, ZT is equal to T times B1 over T. Okay, so it's the ZT we are going to use. So I have here S B1 over S minus S0 Z of S0 over S minus S0. So the ID, so excuse me here. I have here, so it's false what I have written here. It's B of 1 over S0. Okay. So I am interested in, okay, the left differentiability of B at T0 at any T0 belonging to R plus. So what we are going to do is to define S to be 1 over T and S0 to be 1 over T0. Okay? So if I do this job, I obtain what? I obtain, so S is equal to 1 over T, B of 1 over S is equal to T, minus 1 over S0, B of S0 over, okay, 1 over T minus 1 over, so excuse me, so here it's S0 that is equal to 1 over T0. And here I have S0 B 1 over S0 that is equal to, so S0 is equal to 1 over T0. Here I have T0. Okay? So let's continue with my equality here. I can write it this way. It is 1 over T, okay, Bt minus B T0, okay, minus what? Minus B T0 factor of 1 over T0 minus 1 over T, and everything being divided by 1 over T minus 1 over T0. So what I have done here, in fact, I have made appear in this difference here 1 over T minus 1 over T Bt0, and I have added it here, okay, in order to make the equality true. So I introduce Bt0 over T, and if I introduce it, I have to subtract, and so I obtain this equality this way, okay? The numerator here is equal to the numerator here, because I have simplification between this term here and the term here. But if I continue my simplification here, so here I have 1 over T minus 1 over T0. I can put the things into the same denominator, and I obtain T0 Bt minus B T0 over T minus T0. And here I have what? So I see that this term is the inverse of this one. So I obtain plus Bt0. And what can I deduce from this little computation here? I can deduce from this little computation that, excuse me, maybe I will write it here. So let's finish to write it here. I deduce from this computation here that the limit when S decreases toward S0 of Zs minus Z of S0 over S minus S0 is equal to the limit. So when S decreases toward E0, according to my change of variable here, I have T that increase toward T0, and the limit of what? Of this quantity, that is T0 Bt minus Bt0 over T minus T0 plus a constant that is Bt0. So it implies that I know that this limit doesn't exist, okay, according to what I have said at the beginning, because Zt is a Brownian motion, so is nowhere differentiable from the right. So this limit doesn't exist. This limit doesn't exist, so this limit doesn't exist. And what is this limit? But this limit doesn't exist just mean by definition that the Brownian motion Bt is not differentiable from the left, because I increase from the left, okay? I increase from the left, okay, at time T0. That was exactly what I want to prove, okay? So once again, the sketch of the proof is more important than the proof itself, saying that in order to prove that the Brownian motion is nowhere differentiable from the right and from the left, first, using the proposition 1.3.4 I prove that I am not right differentiable at 0, using one transform of the Brownian motion, that is the transform BT0, I prove that I am nowhere right differentiable. And using the transform ZT, I pass from properties concerning the right differentiability to properties concerning the left differentiability. Okay? So from a single fact, the step 1, in fact, I am able to propagate this property to other points from the right and from the left using the transform of the Brownian motion that are itself Brownian motion. Okay, so something that is important. Okay, so to conclude for the moment with the strength properties, okay, we are going to see a last one, and you are going to understand at the end of the session why I study these properties here. That is the fact that the probability that a Brownian trajectory is monotonic in no interval is equal to 1. So the probability that the Brownian trajectory is monotonic in no interval, so no interval, it means that even if you take a very, very small interval, you are never monotonic, okay, in all these intervals, even if they are very, very, very small, with probability 1. So typically it means that when you want to draw the Brownian motion, okay, it seems to be a little bit difficult because, okay, it's not possible for you to increase or to decrease even if you consider a very, very small interval. Okay, so let's continue. So I take this one, duplicate. Me. Erase. Okay, so I want to prove that the probability of this set is 1. In order to prove that the probability of this set is 1, we are going to prove that the probability of its complementary set is equal to 0. And what is the meaning of I am monotonic in no interval? But there exists an interval where I am monotonic. Okay, so if I define by f the following, the union for t strictly greater than s positive infinite here, of the set of the omega belongings to omega such that run motion, so that is bt is monotonic on the interval st. Okay, I said that to prove my result, okay, so to prove this proposition here is equivalent to prove that p of f is equal to 0. Okay, p of f is equal to 0. Why? Because f is the complementary set of the set I have underlined in green, in fact. The set I have underlined in green. Okay? So, in order to simplify a little the things, okay, I can say that to be monotonic is to be decreasing or to be increasing. Okay? And in fact, if I do the job for increasing and the job for decreasing, of course, I will have proved this for BT is monotonic. So we are going to restrict ourselves, okay, on 1/2. But before to do this, just a remark. So I want to prove that P of F is equal to 0. There exists a result, a famous result is probability theory, that tells you that if you have a sequence of sets with probability 0, and a sequence is just a countable family of sets with probability 0, then the union has a probability that is equal to 0. So you deduce from the fact that each set has a proba 0, the fact that the probability of the union is 0, but you have a big constraint, that is your family of sets has to be countable. And here, unfortunately, I don't do countable things here. I work on, okay, the real numbers that are not countable. So it means that I can't apply directly this reasoning. But in fact, I can. Why? Because of the following. So I can say that I have this, in fact. I can restrict myself to the point T and S, but not all the points T and S in the real number, but the T and S that are rational number of exactly the same thing. And why I can do this? I can do this because the Brown motion is continuous. Continuity of the Brownian motion and the fact that, okay, the continuity of the Brown motion and the fact that Q is dense in Q is dense in R. So by the density of the rational and the fact that the Brown trajectory are continuous, okay, then if I am monotonic, or to say that I am monotonic on an interval with rational bounds, or to say that I am monotonic on an interval with real bounds, is completely equivalent in this case. So just be careful, because here, in fact, I don't need a continuity to have this. I need only the fact that Q is dense in R, okay? That would imply that if there exists one intervals with rational bounds on which I am monotonic, of course, it implies that there exists an interval, okay, with real bounds on which I am monotonic, conversely by the density. So here, just be careful. I don't need the continuity of the Brown motion. The only thing I use here is the fact that Q is dense in the real number, okay, to say that, okay, so in other words, in order to have this, I can summarize my argument in the following way. In any real intervals, you have inside an intervals with bounds that are rational numbers, and it comes from the density of the rational number in R, okay? And now what is interesting now is that to prove that P of F is equal to 0, since I have here a union, but a union that is countable, and it changes everything in probability, you know, the countability. P of F equal to 0 is equivalent to the fact that this proba is 0. And it changed a lot because here I have a union and here I have to do the job for a fixed interval st. Okay? I have to do the job for a fixed interval st because by countable union, if this one has a proba 0, okay, if I take sets with proba 0, if I do their countable union, they will have a proba equal to 0 also. Okay, so now I have to focus on this. And according to the remark I have done here, okay, monotonic can be only two things, decreasing or increasing. So to prove that this proba is 0, I have to prove that the probability of the trajectory that are decreasing on this interval is 0, and the probability that the trajectories are increasing on this interval is also 0. Okay, so I will do half of the job. I will do the job for increasing. Okay, that will allow me to conclude because the argument will be the same for decreasing. So I will have this proba equal to 0. And so by countable union, the fact that P of F is equal to 0, that is exactly what I want to prove in the proposition. Okay, so if you have understood, it reminds me to prove only one thing now. It reminds me to prove only one thing, that is to prove that so for the moment, you see that I have used nothing concerning the Brownian motion. The only thing I have used for the moment is the fact that Q is dense in R. So the beginning of my argument, okay, is true for any kind of stochastic process, in fact, okay? I have used nothing about the fact that my process, my underlying process is the Brownian motion. And it's now that we are going to use deeply these facts. So if you have understood, I am interested in this set. On a fixed interval st. Okay. So this one. And I want to prove that the probability of this set is equal to 0. If I prove that the probability of this set is equal to 0, then I will have my result proving that at the end, P of F is equal to 0. And so that the probability that the Brownian trajectory is monotonic in no interval is equal to 1. And now what is interesting is that I work with a fixed interval. So S T. Okay. So what we are going to consider, we are going to consider subdivision, in fact, of this interval. We are going to consider subdivisions with a step size that will be, okay, that will be what? That will be by the length T minus S over N. Okay, so if I do this, an arbitrary point in the subdivision can be written as S plus I T minus S over N. Okay, this one. For I equal to 0, I recover S, and for I equal to N, okay, I obtain this one. So I is between 0 and N. And I say the following. I said that, so I will denote this one by let's say, I can call it capital A as in the lecture's note here. I said that I can write A the following way. It's the intersection for all the n strictly positive of the intersection for n between 0 and n minus 1 of these events. B. So, excuse me, it's not an n here, it's meaningless what I have written. It's I, okay, the index here. B, S plus, I can write it this way, I plus 1 over n t minus s minus b s plus I t minus s over n. So what is the meaning of this one? Oh, excuse me, this one positive. So what is the meaning of what I have written here? So consider all these subdivisions, okay, with arbitrary step size, that is n, okay, can be any integer strictly greater than 0. What I have written here is that the Brownian motion, okay, is increasing over the point of my subdivision. It means that here I am greater than here I am greater than here I am greater than here, and so on, okay? For any point in the subdivision, this is the first part. So if I fix a n, this one means that you are increasing on the point of the subdivision of the picture I have done here. And I want to be increasing for all the point of the subdivision and for all the subdivision, in the sense that for all small n here. And of course, the aim of small m will be to be very big in order to obtain a step size that is very small and to obtain more or less all the point of the interval. So this one means that I am increasing on all subdivision of this type, okay? And for any step size, with my step size that goes to plus to 0 when n goes to plus infinity. And my question is how I can pass from to be increasing everywhere and on to be increasing on the points of all this kind of subdivision. And in fact, the argument to conclude here is just to use that BT is continuous. BT is continuous. Okay, so my trajectories are continuous. And in fact, so do it, okay, it's sufficient to write it, okay, it's not complicated. So since I am continuous, and since the points of these subdivisions here are dense in the interval ST, then to be increasing on all the points of all these type of subdivisions is sufficient to have the fact that I am increasing on the whole interval. It's not true if the process is not continuous. If the process is continuous, okay, I have necessarily this. So you can see this, okay. Of course, this one, if I am increasing on this one, I have this one, and to prove that this one implies this one, but suppose the contrary, and you see that you will have a problem, and the problem will come from the continuity of the Brownian trajectory, okay. Okay. So I am interested in proving that P of A is equal to 0. I remind you that this is my aim, okay? So let's give a name to this one here. I can call it, according to the lecture's note, I will denote this set here as A, I, N, okay? So what can I say? First, I can say that I know the probability of A, I, N. What is this probability? But here I have a Gaussian that is centered. What is the probability that a centered Gaussian is greater than 0? But this probability is equal to 1/2. Because here I have a centered Gaussian, this Brownian increment. So it's here that I use deeply. For the moment, I have just used the continuity of the Brownian trajectory. Now we are going to use more deeply the definition of the Brown motion itself. And first, we are going to use that the increments are centered Gaussian random variables. So the probability that a centered Gaussian is positive is 1/2. Okay. Here, I have the probability of this intersection to compute. And in general, what is nice with the probability of an intersection is that I am able to compute it if I have independence. But I have independence here. Why? Because I consider Brownian increments on intervals, so increments here, increments here, increments here, on intervals that are pairwise disjoints. So you have the independence of all these sets because you know that the Brown motion has independent increments. So the probability of the intersection is equal to the product of the probability. And so here I obtain the probability of each of them being equal to 1/2. I obtain 1/2 to the power n. And to conclude, what I have to say, I said that P of A that is equal to the intersection of all these intersections here is necessarily less than the probability of this intersection, because A is the intersection of all these intersections. So it is less than this one necessarily. And we have proved that this one, so is in fact equal to 1/2 to the power n, with this term that goes to 0 when n goes to plus infinity. So we have P of A equal to 0. F being a countable union of such sets here, P of F is equal to 0. That gives me the proposition 1.3.5, the fact that the trajectory of the Brown motion, okay, are monotonic in no interval with proba 1. Okay, so a very strange property. And you see that the deep argument, okay, is by the use the properties of the Brown motion. Here I use the fact that I am Gaussian. Here I use the fact that I have independent increments, and I use the continuity. So I use everything, okay, in the definition of the Brown motion. So at this stage here, to write this equality, I just need the continuity of the Brown motion. To prove that P of A is equal to 0, I need Gaussianity and independent increments that are true for the Brown motion that allow me to conclude that P of A and so P of F are equal to 0. Okay, so the probability that the Brownian trajectory is monotonic in no interval is equal to 1. So to conclude with the properties of the trajectory of the Brown motion, okay, we are going to study two particular properties that are the quadratic variation and the variation of the Brownian motion, okay? And you will see that typically the position 1.3.6, okay, will be fundamental in the proof of the Ito formula for the Brown motion and in fact for Ito processes, okay? This quadratic variation will play a very, very important role in the following. So maybe before to do this proposition, let's do a little reminder on what is variation and quadratic variation. Okay. So suppose that you have an interval here. 0, 1, for example, and you have a mapping from 0, 1 into R. Okay? We consider subdivisions. Okay, so x0 until xn. Okay, and here I have xi. What I call the variation of f on this subdivision is the following. So the variation of f on my subdivision is this one. So variation of f on the subdivision is the following. The sum of the absolute value of the difference between two consecutive values. In other words, I consider the absolute value of the increments of this mapping on the point of my subdivision, and I do the sum from k equal to 0 to n. It's what I call the variation of f on the subdivision. Okay? What we call the quadratic variation of f on the subdivision, it's the same but you put a square. And we say that f has bounded variations. So let's write this one as VF, this one as VF, let's say V2F, okay? So F as bounded variation is the supremum of VF over all possible subdivision is finite. And we say that as bounded quadratic variations if a V2 of F is finite. Okay, so you take the variations for all possible subdivision, and typically, okay, what interests us is that, okay, what happened for subdivision with a step size that goes towards 0, okay, when I have a very, very big number of points in my subdivision. Okay, so we say that f has a bounded variation on this interval here, 0, 1, if the supremum of the variation over all the subdivision is finite, and quadratic variation if the supremum of the quadratic variation over all the possible subdivision is finite. Okay. So I won't enter into too much details, but I can say the following. There are cases where we are sure that f has finite as bounded variation or bounded quadratic variations. So for the variation, typically, okay, so for the variation, it is very easy to prove that if you have a mapping that is monotonic, then it has bounded variations. If you have a mapping that is differentiable, you have bounded variations. And typically, what we have proved for the Brown motion is that the Brown motion is not monotonic, okay, in no interval with proba 1, okay, and the fact that it is nowhere differentiable. So if I am monotonic and if I am differentiable, I have bounded variation, but unfortunately, it's not the case of the Brown motion, okay? What is more, I can see that, in fact, what we call the quadratic variation is in fact less than the variation. The quadratic variation is less than the variation. Why? Because I put a square here. I put a square, okay? And if I deal with mappings that are regular, that are mappings that are continuous as the Brownian trajectory, okay? If you consider a subdivision with a very small step size, this one is small, but if you take the square, it is very small. So this one is less than this one, okay? This one is less than this one in general, typically when f is continuous and when the step size subdivision is very small. So it's not possible to have typically a mapping that have a finite bounded variation and unbounded quadratic variations. It's not possible because if I have bounded variations, necessarily I have bounded quadratic variations because the quadratic variation is less than the variation. Okay? Okay, well, I have said that in classical analysis, when you are monotonic or when you are differentiable, you have bounded variations, okay? And so you have bounded quadratic variations, but it's not the case of the Brown motion. In the case of the Brown motion, we are going to prove that we have finite quadratic variations, but infinite ones, okay? Finite quadratic variations, but infinite one. It's not in contradiction with what I have said before, because I have said that the quadratic variation is always less than the variation, okay, not the contrary. So you can have finite quadratic variation and infinite variation. Okay, so it's exactly what we are going to prove now. Okay, so I have this one. Okay. Excuse me, I have done a mistake. I have erased my open board. So, excuse me, I have to recover it. Okay. So I hope that I have all my documents. Okay, I hope so. I have to. Yes, I have this one. Okay, so fortunately, I have recovered what I have done. All these tools are new for me, so I try to adapt myself. It's not that simple, but not that complicated, okay? Because we have good tools, but okay. And I erase this. Okay, so I take here a t that is strictly positive. I consider the interval 0t. Okay, and we are going to consider here a particular subdivision, and I will do a comment at the end concerning this. Okay, so I consider subdivision with a step size here that is 1/2 to the power n. Okay, so it's the step size that I denote by Sn. Okay, so it means that my point here, if I take a generic point in my subdivision, I can call it, okay, Ti over 2 to the power n, and I will give a name to this kind of point that will be Ti n. Okay, and we are going to be interested in the quadratic variation of the Brownian motion on this kind of subdivision. So what it will be the sum of the difference between b Ti over n and b Ti minus 1 n square. And I here, how many points in my subdivision? I start from 1 and I finish to the power n. I have 2 to the power n plus 1 point in my subdivision. Okay, and I can do 2 to the power n increments here. Okay, and I call this one z n of t. And my job is to prove that I have the convergence almost sure and in L2 of this random variable towards t when n goes to plus infinity. Okay, I want to prove this one. That is, okay, the quadratic variation of the Brownian motion on an interval of size 0t will be simply the size of the interval, simply the size of the interval. Okay, so first remark, what is the expectation of z and t? What is the expectation of z and t? So by linearity, it's the sum from I equal to 1 to 2 to the power n of the expectation of this term. But what I have here? Here I have a Gaussian, a centered Gaussian, I have a centered Gaussian random variable. So the expectation of the square is simply equal to the variance of b Ti n minus b Ti minus 1 n. And here it's simply the variance of a Gaussian. And I obtain what? I obtain the difference or the size of the interval on which I take the increment, that is Ti over n minus Ti minus 1 over n, and of course the size between 2 points in my subdivision here. So be careful, it's not 1 over n here, it's T over n that I take, T over n. So here I obtain T over 2 to the power n. Okay, and if I do the sum of all these terms, I obtain as an expectation simply T. So I have two convergences to prove here. I have to prove the convergence in L2 and the convergence almost sure. But since the expectation of Znt is equal to T, to prove that Znt converges toward T in L2 is equivalent to prove that the variance of Znt goes to 0 when n goes to plus infinity. I am interested in this variance here because the expectation of Znt is exactly the limit I want to prove in L2. Okay, so I have just to deal with the variance of Znt to prove this convergence in L2 here. Okay, so my job now will be to prove or to compute the variance of Znt. Okay, so what is the variance of Znt? So I will start here. So the variance of Znt is the variance of a sum. Okay, and what I know for the term of the sum, I know that they are independent because we have Brownian increments or intervals that are pairwise division. So in this situation here, the variance of the sum is equal to the sum of the variances. That is not true every time, but that is true here because I deal with Brownian increments, and I know that Brownian increments are independent if I take them on intervals that are pairwise division. So my variance is just here, the sum from I equal to 1 to 2 to the power n of the variance of bti over n minus bti minus 1 n, and I have square here. So it's a b here. bti n minus bti minus 1 r. So this is the variance of this term here. Okay? So what is the variance of bti n minus bti minus 1 n square? So this is, I can write it this way, the variance of the square of something that has a non-distribution. It's a n 0 t over 2n square. Okay, so I can write this one, okay, as t over 2n, the variance of n01 square. Okay, because I can remove the t over n here, so I have a square here, so I can write this one as the square root of t over 2n times n01. I put the square, I obtain exactly what I want, and in fact I have done a mistake here. It's a square that I have here. I have a square here. I have a square. And so what is the variance of n01 square? Well, it is just the expectation of n01 to the power 4 minus the expectation of n01 square. What is the expectation of n01 to the power 4? It is 3. I know. It's what we call the kurtosis of the n01, and minus 1. So I obtain 2 here. Okay, and finally, the variance I am interested in, this one here, is equal to what? It is, okay, 2 times t over 2n square. Okay, so I have this one here. And if I continue, my variance here is the sum of the variances I have computed. Is the sum of the variances I have computed. And what is this equality here? So the variance of all these terms is equal to this one that is independent of I. I have 2 to the power n points in my sum here. So finally, I will have something that is of the form the power n that is equal to t squared over 2n minus 1. And I see that this term goes to 0 when n goes to plus infinity. So what I have proved here, but I have proved half of the job in the proposition 1.3.6. I have proved that the quadratic variation converges toward t in L2. The quadratic variation converges toward t in L2 because I have proved that t is the expectation of Znt. So if I want to prove the convergence in L2, I have to prove that the variance goes to 0. What is this variance? This variance is equal to the sum of the variances because of independence. I compute the variance of each term here that is given by this computation here, and I obtain this term. And I plug this term in my sum to obtain the variance of Znt t squared over 2 to the power n minus 1, okay, that converges towards 0 when n goes to plus infinity. So I have the convergence in L2, okay, and now I have to prove the convergence almost sure of this term here. I have the convergence in L2, and once again, you see that deeply I have used the property of the Brownian motion because I have used, okay, here the fact that I have Gaussian increments, the independence to compute the variance of the sum, and to compute each variance here, the fact that I am Gaussian. So I erase this, okay. And just write that I have proved that Znt converges in L2 toward t when n goes to plus infinity. And I just write that when I have computed the variance of Znt, okay, I have obtained, in order to prove that this term goes to 0, I obtain for the variance t squared over 2 to the power n minus 1 t squared here. Okay, so I want to prove now the convergence almost sure toward t. So let me remind the following. You have a criteria to prove that xn converges toward x almost surely. It's a consequence of the Borel-Canté dilemma that tell you that if for all epsilon strictly positive, the sum of the probability that xn minus x greater than epsilon is finite, so if this infinite sum here is finite, then you have the convergence almost sure. So you have this result at the beginning of the lecture's note, okay? That is a consequence of the Borel-Canté dilemma. So let's see what happened in our situation. In our situation, okay, if I am interested in proving that Znt converges toward t almost surely, I have to be interested in the probability that Znt minus t is greater than epsilon for any epsilon, okay? But in fact, I have a control on the expectation of the square of this term here, okay? So using, in fact, the Chebyshev inequality, I can say that this one is less than what? It's less than the variance of Znt over epsilon square. That is equal to t square over epsilon square 1 over 2 to the power n minus 1. And of course, because this probability is less than this term, and that I know that the sum of this term is finite because I have a geometric sequence here, then the sum of this one, so I can write it this way, is finite. And so I have the convergence almost sure. Okay, because this term is less than this one, and here I have the term, the general term of a sequence with a finite sum, because I have a geometric sequence here that is 1/2 to the power n minus 1. Okay, so I have proved from this argument here and from the Borel-Cantelli lemma here, implying this fact here, that I have the almost sure convergence. I have the almost sure convergence. So just a remark, because, okay, if you have a look on my statement here, I have taken a very, very particular subdivision. That is this one with 2 to the power n, with step size that is t over 2 to the power n. It's what I have said here. Okay, I have a step size in my subdivision that is t over 2 to the power n. What happens if I change the step size of my subdivision? So where I have used this, I have used this, okay, here, because I see that I obtain, okay, something that is in relation with the step size here. And in fact, I can prove very basically, you can do the proof at home, it's exactly the same computation, that if you have a step size that goes towards 0, simply without doing this particular assumption of the step size of my subdivision, if Sn, my step size, goes to 0, the variance will go to 0, because here you will make appear something that is in relation with the step size of your subdivision. So to prove that I have the convergence in L2, in fact, the only thing I need is that the step size of the subdivision converges towards 0. Okay, so I can extend the convergence in L2 results in this proposition to more general subdivision, just supposing that the step size of my subdivision converges towards 0. For the convergence in L2, for the convergence almost sure, what I have used in the comparison for the convergence almost sure, I have used the Chebyshev inequality here. And what we have used, I have used that if I consider the step size considered previously, that are this one, if I take the infinite sum of this step size, this infinite sum is finite, okay? This infinite sum is finite for the step size. So it means that if you do as an hypothesis, not this very, very particular step size here, but a step size such that the infinite sum of the step size is finite, you are able to prove the convergence almost sure. So in fact, the proof I have done here is more general than what the statement can means, because what I have proved is okay for convergence in L2, okay for subdivision with step size converging towards 0, convergence almost sure, okay for subdivision with step size fulfilling the property that the sum of the step size is finite. Okay, I have this. So to conclude with the properties of the trajectory of the Brownian motion, just let's prove a corollary of this result here. Okay. That is the fact that in spite of the fact that the Brownian motion has quadratic variations that are finite and that are in fact equal to the length of the intervals on which you consider the variations, it has infinite variations, in fact. So I have finite quadratic variation, but infinite variations. And I repeat that it is not something that is incompatible, because the quadratic variation is smaller than the variation. So the quadratic variation may be finite and the variation may be infinite without any kind of problem. Okay. So I want to prove this. Okay, that the variation of the Brownian motion, so here I remove the square, so it is the variation, here I have a square. The variation of the Brownian motion on my subdivision converges toward, almost surely toward plus infinity, okay, for this one. Okay, so let's suppose the contrary. So to say that I am with a limit equal to plus infinity p almost surely, so if I suppose the contrary, I prove the corollary 1.3.2 here. Suppose the contrary. So the set on which I converge toward probability, the set on which I converge toward plus infinity is proba 1. Okay. To suppose the contrary is that the probability of the set, okay, on which the limit when n goes to plus infinity of the variation is finite. So if I suppose the contrary, the probability of this set is strictly positive, because it implies that if this one doesn't hold, its probability is strictly less than 1, and so the probability of its complementary set, that is exactly this one, is strictly greater than 0. But what I have here, so I have to make the link between this one and this one. So let's write the quadratic variation. I can say the following, okay? The quadratic variation is less than the following. Then the maximum for j between 1 and 2 to the power n of these terms, btgn minus btg minus 1 n multiply by the variations. Okay, I just say that I separate this square in the product of this term and this term, okay, itself. I said that the first is less than the maximum and I keep the second, okay, so that's why I obtain this one. Okay, it's not complicated to obtain this. Okay, what I know that the trajectory of the Brownian motion are continuous. So the Brownian motion is continuous on 0 capital T. If it is continuous on a compact set, it is uniformly continuous. Okay? And what is the meaning of uniform continuity here? Keep in mind that my T and G are the point of a subdivision with a step size that is T over 2 to the power n. Okay? So if I consider this difference here, and if I make n goes to plus infinity, this term goes to 0. But in fact, this term goes to 0 uniformly over the point of my subdivision because my trajectory are uniformly continuous. So when n goes to plus infinity, I can say that this term here goes to 0 when n goes to plus infinity. I repeat why, because when n goes to plus infinity, the points of the subdivision are very close, implying that the Brownian motion at these points are also very close because I have the continuity on the interval and so the continuity. So I know that what I have inside converges towards 0 by continuity, but I can take the maximum because this convergence is uniform by the uniform continuity property of the trajectory on this compact set. So this term goes to 0 by the uniform continuity of the trajectory of the Brownian motion. What I know from this one? From this one, I know that this one converges toward t, almost surely. It's the previous proposition. The quadratic variation of the Brownian motion converges almost surely toward t. But I have a problem here. I have a problem because if I suppose that the probability that the limit of this one is finite is strictly positive, that is, the probability for this one to be convergent is strictly positive. So on the set for which this one is convergent, what happened for this inequality? I will obtain that t is less than something that goes to 0 multiplied by something that is convergent, that is t less than 0. If I pass to the limit in the previous inequality, supposing that I have this, so if this term is convergent with a probability that is strictly positive, if I multiply by 0, I obtain 0. And so since this one converges toward t, I obtain that t is less than 0, but it is not possible because I have supposed that t is strictly positive, okay? So I have proved this way that it's not possible for the Brownian motion to have, in fact, infinite variations because it has finite quadratic variation and because it is continuous. So in fact, here, I don't really use the properties, all the property of the Brownian motion. I just use the fact that it has continuous trajectories, in fact, and it's a general result of classical analysis to say that if you have a mapping that is continuous, okay, if it has a finite quadratic variation, necessarily the variation is not finite. It's exactly what I have proved here for the Brownian motion. Okay, so I think that I will finish the course for today this way. And I will organize, so next Tuesday, a session of questions in order to answer in particular what I have done today. So see you next week. Bye-bye.